Welcome everyone to today's video. So today we'll be covering a method to solve first order differential equations called the separation of variables. Okay, so before we do dig right into the content for today, let's just go over a few basic definitions to make sure that we're all on the same page. So what exactly is an ODE? So an ODE, or an ordinary differential equation, is a differential equation that contains one or more functions of one independent variable and its derivatives of those functions, okay? So the emphasis there is that there's only one independent variable. That's what makes it an ordinary differential equation. And that's how we define an ODE. So what exactly is a first order differential equation? Well, all the order actually indicates is it just says, well, what derivative are we taking? So if it's a first order differential equation, then we are only working with first derivatives. If it was a second order differential equation, then we've got second derivatives in there. So the method of separation of variables is going to be very, very useful for a lot of different ODEs, but today we'll be focusing on simply just first order differential equations. So when can we actually use the method of separation of variables? If we have some differential equation that we can write out as f of xy is equal to dy on dx. And that's something that we should be very familiar with. This is our standard definition of a differential equation. But when I can separate the variables, what we'll find that I'm able to do is I can rewrite this whole expression as simply h of x, so some other function, not f, h of x plus f of y dy dx equal to 0. So if we can write it in this form, where we have just a function of x and a function of y completely separated, then we can use the method of separation of variables. And what this then can be rewritten as is simply h of x dx plus f of y dy equal to 0. And as soon as we have our problem in this form, then that's when we can get right into the business end of the method of separation of variables. Okay, so let's have a quick look at our first example here. So for our first problem, we're given xy prime is equal to 1 minus y squared all to the power of a half. Okay, so there's one really quick thing that we can do to make this problem look a lot more approachable, and that is to write this as dy on dx instead of y prime. So let's do that real quick, and we're left with x dy dx equals, again, 1 minus y squared all to the half. Okay, so if we remember, what we wanted to do earlier was we wanted to rewrite this entire problem in a form where we have just a function of x and a function of y completely separated. And so we can actually do that pretty quickly here. So all we need to do is, in essence, it's going to look like we're just timesing the dx up to the other side, dividing by the x, and then bringing down this right-hand side onto the left-hand side. And so what that looks like is essentially 1 over 1 minus y squared all to the half dy is equal to 1 over x dx. Okay, fantastic. So far, so good. It should be fairly intuitive, but let's see what happens next. So one thing we need to be really careful of is the restrictions to our domain or range. So one thing that we'll notice here is that we have an x on the denominator, and then on the other side we've got a 1 minus y squared all square rooted. So what does this mean? First of all, 1 over x, so that means that logically x should never be equal to 0. Okay, good. So we'll work with that bit of information there. The other thing that we can determine from having the 1 over 1 minus y squared all square root is that y squared should never be greater than 1, because otherwise we're taking the square root of a negative number, and for now we're just working in the real domain. So what that means in terms of restrictions for y is that the absolute value of y must always be less than 1. And let's double check, why isn't it less than or equal to 1? Because if y is equal to 1, then this just goes as 1 minus 1, and then the whole thing blows up. So we'll leave that as x cannot be equal to 0, and the absolute value of y must be less than 1. So for now, we're just going to put those in a box, just that way we can keep that a bit of information for later at the end of the question. Okay, so all we need to do now, though, is simply integrate both sides, and that's nothing that we can't handle. So you might recognize this on the left-hand side. That will just integrate and become arc sine of y. And then our right-hand side simply becomes natural log of x plus a constant term, okay? So that constant can be pretty much any real number, unless it's defined by an earlier on initial condition, okay? So for now, I'm just going to say that C1 is any real number. All right. Okay, let's keep going. So now all we need to do is solve for y, and so this is a fairly straightforward problem to do that for. And so we can just say that y is equal to sine of the natural log of x plus this constant term c1. Alright, so let's have a quick look at our second problem here. So our second problem, again, isn't anything too crazy just yet. So we'll have dy on dx is equal to x cubed over 1 plus y squared. So we can pretty quickly rearrange this to separate our variables. And so what we get when we do that is just 1 plus y squared dy is equal to x cubed dx. Okay, fantastic. So again, let's just quickly check if there's going to be any restrictions. And I think for this one, it's actually going to be pretty good because there's nowhere that it's going to blow up. There's no strange domains in play here. So we should be pretty good to go. And our next step is simply, again, to integrate. Okay, so after we've integrated, left-hand side will become y plus y cubed on 3 equals to x to the 4 over 4 plus that constant term. And it doesn't actually matter which side of the equation we put that constant term on, because that could be a positive or a negative constant. So feel free to flip it onto any side, but I'll always write it as just plus constant sub 1. Okay, and at this point here, we can't actually simplify this much further. All we can do, if we would like, is to bring everything over to one side, just so that way it looks a little bit nicer when we write our final solution. So we can rewrite it as y plus y cubed over 3 minus x to the 4 over 4 plus c1 equals 0. And that's it. All right, perfect. And so again, just to reiterate, I can write plus c1 because we don't exactly know what c is. It can be a positive, it can be a negative, so I am free to define it as just a simply positive c1 over here. All right, let's move on to our third example. So the third problem is a little bit trickier and a little bit more interesting than the ones we've seen so far. So let's work with a new set of variables. So we'll have dr on d theta equal to r squared over theta. But what I'm going to define here is an initial condition. So I'm going to say that r of 1 is equal to 2. Okay, so that's our initial condition, and it's extremely important for us to remember that at the end of the question. Okay, so again, separation of the variables. What we want is to have all the r's on one side, all the thetas on one side. So to do that here, what it ends up becoming is just 1 over r squared dr is equal to 1 over theta d theta. And again, this is the stage at which I like to quickly check if there's going to be any restrictions. And so clearly, what we can see is that theta cannot be equal to 0, and r squared can also not be equal to 0. And you can just rewrite that as just r cannot be equal to 0. Okay, excellent. So again, at this stage, all we need to do is just quickly integrate those two terms. And what pops out is simply going to be negative 1 over r equal to the natural logarithm of theta plus some constant term c1. Okay, so at this point, all we need to do is just quickly solve for r, which isn't very difficult algebra. All we need to do is just bring the r up to the other side and then bring this side down to the denominator. And so what we see is we'll be left with r equals, I'm going to write negative 1 over the natural logarithm of theta plus this constant term c1. Okay, so at the start of the equation, we had an initial condition that r of 1 is equal to 2. So what I'm going to do is I'm going to go through, and anytime I see theta, I'm going to fill it out as a 1, and anytime I see r, I'll rewrite it with a 2. So this equation now becomes 2 equals negative 1 over the natural logarithm of 1 plus c1. Okay, so we can reevaluate the natural logarithm of 1 as simply being 0. And so what we see is that we have that 2 is equal to negative 1 over c1. And so we can solve this pretty quickly and have that c1 is equal to negative 1/2. Okay, excellent. And so now that we have our c1 term defined, all that's left for us to do is to go and quickly put that back into the original problem and rewrite it as r is equal to negative 1 over natural logarithm of theta minus 1/2. And I can, of course, just quickly absorb that top negative into the denominator, and then I'm left with r is equal to 1 over 1/2 minus natural logarithm of theta. And that's our problem done. Alright, excellent. So let's move on to our fourth example now. So this one is going to be quite difficult, and we'll actually need to use another technique, a substitution technique. So we've got dy dx equal to 3y squared minus x squared, all divided by 2xy. Okay. So right off the bat, you can see that this one's going to be quite a bit more challenging to try and solve using the method of separation of variables. And the reason for that is because everything has an x, y grouped together, so it's going to be much more difficult for us to manage here. And so many people might look at this and think, oh, well, I might use the difference of two squares and we can see what happens. So we would have root 3y plus x, root 3y, minus x, all divided by 2xy, and that doesn't actually help us whatsoever here, so we're going to completely forget that. What will help us is using a little substitution called a v substitution here. So the v substitution is where we will introduce a new function, v, and v is going to be equal to y over x. Okay, so what that means is that we can redefine y as being equal to xv. Okay, and I should explicitly write v as a function of x as such, but that gets quite messy, so for now we'll just leave it as v, but as long as you know that v is a function of x, we should be fine. Okay, so if y is equal to xv, then let's have a quick think about, well, what would dy dx be in this case? Well, so dy dx, that's going to be the same thing as taking d dx of x times v, where v is the function of x. So we'll need to use our product rule here. So this ends up, we can write this as dx dx v plus x dv dx, where we see that dx dx, well, that makes no sense, so we can just get rid of that. There's no point in rewriting a 1 in there. So we can now write dy dx equals to v plus x dv dx. Okay, so let's go through now. We've got a whole list of new variables that we can rewrite this problem with, and let's see what we get. So instead of writing dy dx, I'm now going to write, for our left hand side, v plus x dv dx equals to, and for our right hand side, we'll say 3 times, so y is xv, xv squared minus x squared, all divided by 2x xv for that y. Okay, let's quickly see if we can simplify the right hand side at all. So we will have 3 times x squared v squared, so we'll write that out as 3x squared v squared minus the x squared, all divided by 2x squared v. Okay, so what we can see right away, and hopefully it's fairly obvious, is that we actually have a factor of x squared that we can take right out of this whole equation. And what we're left with is simply 3v squared minus 1 over 2v. So now it's looking a lot more manageable for us to actually work with. Alright, so I'm just going to take this down to get a bit more space, and let's see what we have. So we had v plus x dv dx was equal to, we had 3v minus 1 over 2v. Oops, sorry, 3v squared. Alright, excellent. So our next step here would be to simply move that v across, and we're left with x dv dx equals to 3v squared minus 1 all over 2v, subtract v. Okay, let's make this so that way we can actually work with this, so we'll have a common denominator. So I'll just times this by 2v on 2v, and then the right hand side will simplify out to become 3v squared minus 1 minus 2v squared, all divided by 2v, x dv on dx on the left hand side. And now it is looking good, because what we can clearly see now is that our left hand side we've got an x, that's the only side we've got an x, and then our right hand side we've got only v's. So finally we're at the point where we can start thinking about using our method of separation of variables and start integrating and actually solve this ODE. Okay, so let's keep going. So what we want to do now is get these on either sides. So we'll want to bring the x up to the other side and the v's onto the left hand side. So this will now look like 2v over v squared minus 1 dv equals to 1 over x dx. Oof, okay, so again, this is the point at which I always want to make sure that I'm checking to see if there's going to be any restrictions. So clearly, again, we can't have x equal to 0, and it makes no sense for v squared, that cannot be equal to 1, because again, our denominators would blow up. So we'll say that x cannot be equal to 0, v squared cannot be equal to 1, and now let's keep going. So now at this point, we can integrate with respect to v on the left hand side and x on the right hand side. And so this becomes a pretty straightforward integral. So we're left with the natural log of v squared minus 1 is equal to the natural logarithm of x, and then plus some constant term, and we'll call that c1. Okay, so now we want to solve for v, ideally in this situation, so that way we can get back to y, the dependent variable. So let's keep going. So we'll take the exponential of both sides, and then we're left with, well, the exponentials will cancel out, so then all we're left with is v squared minus 1 equals x e to the c1, and then I can just rewrite e to the c1, change that up a bit, and just write it as c sub 2. Alright, so let's keep going. Let's keep solving for v, and what we need to remember is that v was defined earlier as y over x. So you can do this at this point here if you would like, where we can just quickly redefine this as, instead of v squared equals x c2 plus 1, we can now write that y squared on x squared is equal to x c2 plus 1. Alright, fantastic. So again, we're just looking to solve for y here, so we'll keep going. We'll multiply both sides by x squared, and we have y squared is equal to x cubed c2 plus x squared rather. And at this point here, all we need to do is take the square root of both sides, and then we are done. So we can say that y is equal to plus or minus the square root of x cubed c2 plus x squared. And so you can also take out that factor of the x squared and chuck that out the front. So all you're left with then is plus or minus x square root x c2 plus 1. And that is the solution to our initial problem, which, just as a quick reminder, was dy dx equals 3y squared minus x squared over 2xy. So that was our problem, and this was our solution.